I'd like to look at some examples from section 2.5 with you. Here we're looking at limits at infinity. Okay, in section 2.4 we were talking about infinite limits. Here we're looking at what happens as x gets larger and larger and larger, positive or negative, and what that does to the expression that we're interested in. Specifically, these examples deal with limits at infinity for rational functions. A rational function, as we know, is a polynomial over a polynomial. And I want to go through some algebraic steps with you for this first one, but then I'm going to point out that there's a shortcut that we can use when we're dealing with rational functions, and that's something that's discussed in this section. So what we can do in terms of algebra is we can divide the numerator and denominator by the largest power of x that we see from the denominator. Okay, so actually let me back here, divide by x cubed, both in the numerator and denominator. Okay, and since we're doing the same thing to both numerator and denominator, we're not changing the limit. But it is going to change how we write the expression. So now we're going to have 14 plus 3 over x minus 2 over x squared divided by 21 plus 1 over x plus 2 over x squared plus 1 over x cubed. Okay, and the key thing about this expression, the reason that we took that algebraic step, is to get us all those expressions where we have, 1 over x squared, 1 over x cubed, or a constant multiple of any of those things. What's important about those is as x goes to infinity, or if x were going to negative infinity for that matter, all of those expressions, besides the constant ones we see out in front, would tend to 0. Okay, so this is going to 0, this is going to 0, etc. Okay, that's something that's discussed in section 2.5, and if you, just to briefly explain why, what's happening is that we have a non-zero constant over something that's getting larger and larger and larger, whether positive or negative, and that's going to make the whole thing go to 0. And so what we're left with in our limit is just that constant 14 over 21, okay, which is 2/3. So that's the limit in this case. Now here's the shortcut I was referring to earlier. If we look back at the original expression that we're taking the limit of, and we compare the highest power of x from the numerator with the highest power of x in the denominator, that is, if we compare the degree of the polynomial in the numerator with the degree of the polynomial in the denominator, they're the same. And whenever the degrees are the same, and you're taking a limit as x goes to infinity or negative infinity, then the limit is going to be just the leading coefficient over the leading coefficient. Okay, so we could have just skipped right to 14 over 21 by observing that we have the same degree. Okay, so here we've got an example where the degrees are different, number 26, but we're still taking a limit as x goes to infinity. If the degree in the denominator is bigger, what's always going to be true is that this limit will be 0. And we could go through similar algebraic steps to what we did in 25 to see that. One way to understand kind of informally why that might make sense is that the denominator is growing faster than the numerator. And it's enough so that the entire expression is going to go towards 0 in the long run. Finally, if we look at this last one, we have another rational function, polynomial over polynomial. This time the limit as x approaches negative infinity. That doesn't actually change anything about our answer here. Our answers to 25 and 26 would have been the same if we were approaching negative infinity. Whenever the degree in the numerator is bigger than the degree in the denominator, what will be true is that the limit does not exist. Now, in this course, we don't get into the concept of oblique asymptotes. That is something that would apply to this particular example. The degree of the numerator is 1 greater than the degree of the denominator. So that does have a certain kind of asymptote, but it's not a horizontal line. And we're going to say that this limit does not exist. Okay, thanks for watching, and I'll see you in the next video.